All right, let's get started. Hi, my name is Frelich. I'm a senior systems engineer with F5. I've been with F5 about 6 years. I handle major accounts out of the West Coast, so I work with a lot of the large web monsters and larger corporations out of the West. Prior to that, I spent about 20 years as a network and security architect for Fortune 500, Fortune 100 firms. So I've been on your side of the fence for a long time before joining F5. And then I have my distinguished colleague, strategic architect, Mudit Tyagi. He is focused primarily on our DDoS solutions, and we're fortunate enough to have him here. Just kind of an agenda, an overview of what we're going to talk about. We're going to talk about why we're here, right? Otherwise, we got no framework to start off of. We're going to talk about a strategy for mitigating DDoS attacks. We're going to identify and walk through some of the critical infrastructure points, and then we're going to cover a lot of mitigation strategies. So unfortunately, the title of this class is a little bit more marketing than we liked. It focused more on F5, and we're going to give you strategies and tools to go forward and not specifically tell you, do this here, buy this product here, right? And we're going to cover a demo of Layer 7 behavioral DDoS mitigation, which is a very strategic tool for mitigating attacks. And then we're going to review where you're going to look at applying those and strategies for mitigating those attacks. And then last, we're just going to cover and then sum it all up by giving you some bullet points for assessing your posture and your health against mitigating DDoS. So why, of course, are we here? DDoS seems to be on the top of everybody's mind. Not only is it reputational risk, it's financial risk. Next to credit theft, it seems to be the biggest worry of your CISOs and CIOs, right? So what does F5 know about mitigating DDoS attacks? Well, once we had a server. Way back in the day, finance went and spent a bunch of money, bought you this beautiful shiny server. They loaded the application on it, and there was a little party, and everybody was really happy with it, and it had a handful of users. And those handful of users were really, really happy with it, and they started spreading the word. And the next thing you know, there's thousands of users joining it. And then your data centers started popping up, right? So how did we needed a method for distributing traffic across all of those new servers, those application servers. You can't just hit one anymore. Referencing IP addresses in DNS didn't work. So that's where F5 came in. So that's why we're really here. DDoS mitigation is about application delivery. The astute author of this quote was, yeah, we'll just leave it at that. No, that's really what it's all about, right? If you can't deliver your application, then what's the point, right? If we just block things, like the traditional security model, we're just going to, cut it off here. Well, security guy said no. Well, I have to deliver my application, right? That's why we're all in business. So quick review of the types of DDoS attacks or DOS attacks in general, right? You've got your volumetric. These are things that require a little bit of effort, or they may be distributed. You can have script kiddies running attacks that can easily overwhelm infrastructure, right? You've got spoofing IP addresses, very common, right? I can do amplifications, so I'll make a small DNS query, and the response is huge, and it floods your pipe, right? Or we just have millions of little bot zombies all over the world, and we just have all of them and start attacking at the same time, right? We can overload connection tables, etc. Then you have your more computationally intensive type, more sophisticated attacks. You have application layer attacks. They require little effort, but there's a big return, right? Slow post, slow read, right? I can do it with a VM, and I can take down an Apache application server. You've got exploiting expensive queries, right? There's a technique where they'll crawl your website and they'll discover all of the different URLs and they'll say, hey, look, this one takes 10 milliseconds to respond. This one takes 100 milliseconds to respond. So then I just start attacking that one, right? And then I start, because I know that's causing stress on the server, and I keep banging away at that with all of my resources, and it doesn't take as much. And then, of course, you've got hybrid attacks. A lot of times we see attackers flooding the network with volumetric attacks so they can sneak in and do other nefarious things, right? Or they can launch those smaller attacks that you can't see because there's just so much volume. Additionally, they may actually try and exploit your server, exploit your database, right? So my challenge to you is think differently. I want you to think from the inside out, right? There's always this answer or this instinct that we want to get a really big box and put it right on our edge and it's going to solve all of our problems. I experienced a little bit of a DDoS attack myself this morning. I had a slide that had Bullwinkle pulling the lion out of his hat, and I was going to say, you know, there's no magic answer, one magic answer for all that. I'd love to tell you, buy a big F5 box and put it in front of your infrastructure and you're good to go. The DDoS attack was marketing telling me I couldn't use that slide for copyright reasons. So I fell back to suckering my daughters into turning their clothes inside out and posing for a picture. The third one refused to actually be put on camera, but I think she's the smarter of the three. But really, starting at the inside, right? Start with your applications. Do an application assessment. Understand what the application risk is, what the value of it is. Is it a high value target, right? If it's just some corner case application that's sitting over there, is it really going to be worth your time investing in mitigating it? And how much time are you going to apply towards that, right? But it might be sitting in a shared infrastructure with a very high value target, right? So start thinking along those lines. And start performing baselines of your traffic, right? Or your applications. We used to do this a lot, and it just seems like it doesn't happen as much anymore, is that people are building baselines and trends for their applications. One of the great tools for that is we have analytics. AVR is a module that runs on the big IP. It collects all the response times, client and server side, and it's free, it's there, but nobody ever really turns it on. It's like, this is how you start building those baselines and you start planning, because DDoS attack doesn't necessarily mean you're under attack. What happens if you have a Black Friday sale and you just don't have enough resources? You didn't plan enough for that, right? So there really is no magic rabbit. There's got to be a lot more thought. But you start at the application and start working your way outside. Another thing is, right, are you using SAML or LDAP for login? Is those east-west traffic flows, they're rarely identified. You build your application map and it's all, here's your web servers and your database servers and everything else, but then there's this one call off to the side that's hitting your LDAP server, and it's actually owned by a completely different infrastructure team, but it's susceptible, right? Somebody or some other application is using it and it gets attacked. So you really need to have these traffic flows mapped out in your mind and ideally on paper so you can trace down these problems and plan for it accordingly. So looking at this inside-out paradigm, right? We're going to kind of cover a lot of the different vulnerabilities and the components and limitations that each of those have, right? So application vulnerabilities themselves, right? We'd like to all think that we write perfect code. I know F5 does. We don't have any bugs. Right? Just like your application developers, they don't necessarily write the most perfect code day one, right? So these are all CPU and memory, right? Have these sized the application properly, right? SSL, if you're doing SSL re-encryption to the application, do you have enough performance to be able to handle that? SSL is heavy math. There's a reason why F5 has put dedicated SSL chips in boxes for a long time. It's because we take and offload the heavy math so our general purpose CPU can do more complex things, right? Concurrent thresholds, right? Your DBs all have thresholds. I'm sure we've all experienced stored queries that ended up bringing down the entire database server just because stored procedures that somebody left in place and it wasn't very efficient, and every once in a while it would just get hit and take down the database server. Next, pushing that further downstream or further off-prem, you start looking at your firewalls and your load balancer, right? These are connection-oriented devices, right? They want to maintain state and distribute the application traffic accordingly. So they do still have limited memory, right? You look at some of our boxes from maybe 10 years ago, we had small amounts of memory, but we managed it really, really well. But either way, there's still a vulnerability, or at least a point of risk, right? So you've got your CPU and memory, SSL, right? Once again, back to we're doing SSL handshakes. How many of those can we handle concurrently? Now moving a little bit further down the line, you've got your internet pipe, right? That's the easiest thing to overwhelm with those distributed volumetric attacks. Additionally, you've got routing tables, right? You start causing routing table churn. The CPUs on your routers can get buried. You've got control plane, right? You can start, if you're not doing control plane policing on your routers, the data plane can get overwhelmed and you start losing your BGP sessions, and your BGP starts flapping internally and suddenly you're offline, right? And of course, once again, even routers have vulnerabilities. So how are you protecting them? And then lastly, once you get to a solution where you've pushed it all the way past your edge and you start leveraging content delivery networks and DDoS scrubbing in the cloud, these shared risk models, right, where you can't afford to have this large pipe that's 6 terabytes wide. It doesn't make sense to go and invest in that for when 90% of the time your bandwidth is maybe 100 meg, right? So you leverage cloud scrubbers, which have this shared risk model. But the thing is you're still in a risk pool, right? And how do you understand when you are under attack? Well, stress on the service. That's the most common, the easiest way to look at what is the impact of an attack. It's because the application is not being delivered efficiently. Stress doesn't necessarily mean an attack, or it could be a self-inflicted one, like the Black Friday sales, or a new marketing campaign that went out they didn't tell you about, and suddenly you've got an influx of server traffic, and you're like, what happened, right? But in the end, stress is about bad user experience. Stress does equal a denial of service attack, whether it's intentional or not. If the application is not being delivered, then it's a denial of service and you have stress. So with that,
okay, so thank you. So what I wanted to do now is have a conversation with all of you. So we can get all sorts of attacks. We can get TCP SYN floods, we can get push floods, we can get mixed flag floods, we can get UDP floods, we can get ICMP floods, then we can get reflection attacks, amplification attacks using various protocols. Brendan showed us different portions of the infrastructure can get attacked and cause bad experience for the user. And one good way to figure out that, hey, the users are about to have really bad experience is to measure how is the service doing by looking at the packets that are going to the service before the users begin to see bad experience. So the trick there is when we're computing stress on the service, we're actually looking at response times and latencies back and forth between the request that comes from the client going to the server. How long is it taking the server to respond to that request, right? So essentially, by measuring stress on the service, we're measuring the experience that the user is about to have. Okay, so let's say the service is getting stressed out. Now, what is it that we should do? What is the best strategy? How should we block? So this is the conversation I want to have with you all. So our goal is actually not to block anything if we can bring the stress on the service down, which means if we can improve the user's experience without blocking anything. As a DDoS device, we're not a firewall, which is a default deny device, and you open only the holes that you want to let through. We are a default open mechanism, where DDoS mechanisms are typically default open. Their goal is to let everything through unless there's a problem, right? And it has to discover that problem on its own and do it accurately. If the problem is not discovered accurately, and we start taking mitigation action, we could be causing false positives, right? So we actually don't want to drop anything. The first thing that I would do, forget the technology, just from a strategy point of view, I tell everybody, slow down. Let my server breathe, right? If that doesn't work, then I say, okay, I want to keep my humans going through, but any bots that I see coming to the service, I want to start blocking those. And even there, I want to be judicious. I want to block the bad bots and let the good bots through. Otherwise, you may actually disturb the service, right? Notice, no sledgehammers here. I'm trying to be precise, right? So now, the next thing is I want to use machine learning and compute exactly the anomaly. And I'll show you a demo of this. Compute exactly the anomaly that is causing high stress on the service. And I want to drop that particular anomalous traffic. So it would be the case in this scenario where a human user is coming from a machine and their session goes through, but the bot on their machine, which is trying to launch an attack, we begin to block the bot, right? So again, no sledgehammers here. I'm trying to be surgical, trying to keep the service alive, right? So then the next thing we do, okay, this didn't work. All right, so what, Brendan pointed out, one of the common attacks is that the attacker figures out which URL is a heavy URL that causes a lot of churn in the back end. So let me actually start controlling that first. And then, the hacker may be doing low and slow connections. Let me find those and drop those first. Again, notice my spirit is I'm trying not to punish everybody. I'm trying to be surgical in who I stop, right? So now, if these surgical mechanisms didn't work, then the next thing that I can do is I can say, okay, what is my most attacked URI right now? Let me rate limit that. That doesn't work. Then I might start doing source IP-based controls, which are very dangerous because you may have a mega proxy. And all your users are coming from behind this source IP, including the attacker. So notice, that's my step number 7, right? I try to do intelligent mitigation prior to doing this step. And then finally, I come to what is the common in the market, what people typically think about when they think about mitigating DOS. They think about doing rate limiting connections, rate limiting of requests, rate limiting based on specific source IPs, rate limiting of bandwidth. The item number 8 is what people think about, but it is not, in my opinion, the most effective mechanism. It might give you pain relief, so all your resources can breathe, but then you, again, have to start opening up the service and not block the users. So what I call here is, notice I've not mentioned any technologies. These are strategies. This is the ideal response that we want to have, right? So if you do mitigation intelligently, that keeps the false positives low. And the other thing it does is it keeps the good traffic coming in, and it surgically tries to take the bad traffic out. And that, I think, is very, very important to sort of internalize. So I'll take 30 seconds here. Do you agree, disagree with this approach? I haven't talked about technology. This is just an approach. This is what we want. How many people here fight DDoS or do security configurations? Okay, and so you agree with me that it's a default open system, right? We're not trying to block, but we are trying to block surgically. And typically, those of you who have actually fought off DDoS operationally, one of the things that you find, one of the difficulties is you start blocking too much and you start dropping too much. I know of a case where service provider and the DOS operational team was not very experienced, and there was an attack on UDP, actually a DNS attack. They blocked all UDP, and everything stopped working, right? So this is the critical thing to keep in mind. Intelligent mitigation is critical. Okay, so when it comes to detection, one of the things that I found as I talk to customers and to partners, detection is not very sophisticated. The tools out there are not very sophisticated. Typically, people learn that their service is DOSed because actual users of the service start saying, hey, I cannot get there. Some people are a little bit more advanced, and they use synthetic users as application testers. And those synthetic users begin to fail, and they say, something is wrong, right? So the other traditional techniques for detecting that we may be under attack is to actually set thresholds manually, right? So you will say, okay, so many, I have an example up there. So, if you see more than X number of packets per second of TCP with push flag set, consider that to be an anomaly, right? So your detection is extremely basic, right? So some human is coming up with thresholds that you set for these specific vectors. And the other approach is, hey, if I see an instantaneous change, a rapid change in the packets per second that match a particular vector, I was seeing only X number of packets per second of TCP push, and suddenly I see 500% change. Consider that to be an attack, right? These traditional techniques are fraught with a lot of error. Anyone who does DDoS fighting will tell you that trying to gauge exactly what the value for a threshold should be, where you think that you are under attack, is an extremely difficult thing to do, and it's not humanly possible to get it right. So there are improvements to these techniques, and I will talk about one of them, where you start to automate the determination of the thresholds for each vector, right? And then the state of the art is monitor your service. If the service is getting stressed out, that is the most definitive indication that you're under attack. It may be the case that the amount of traffic going to the service increases because someone did a successful marketing campaign, and it's good users who are coming to the server, and you had taken appropriate measures. You were expecting that the amount of traffic coming to the service is going to increase. Well, if on the DDoS device you forgot to change the threshold, right? Legitimate traffic would look like an attack to you, right? However, if you're using stress-based determination of attack, that's accurate because the system is saying, yes, I see much more load coming in. I see much more traffic coming in, but the service is functioning fine. The latency from the server is performing fine. So this is just the new normal that, someone had done a massive marketing campaign and we're just seeing a whole lot more traffic. Notice, with that, the technique of specifying manual thresholds is fraught with error, right? Does this make sense? Excellent. So, okay, mitigation. Again, typically, we spoke about it a little bit when we discussed the intelligent mitigation, which is what we want. But so far, what you end up getting, the traditional mitigation schemes are very basic and again fraught with error. So there's bandwidth rate limiting. This is very bad because yes, you reduce the amount of traffic coming to your service, but who are you dropping? You're dropping good users and bad users, right? So it might stop it might be the thing to do at the moment because if you don't do it, your infrastructure begins to reboot, right? But you're still taking a hit. You're dropping good and bad users when you're just doing blind bandwidth rate limiting, right? Then you can do, you can go a little bit further and you can do vector-based blocking. So on your firewall at the very edge, you have certain ports that are open. And if someone starts to send, port 55 on your firewall on your public IP is not open, and the attacker is sending a flood to that port, sure, block it. That's safe. But then you start doing vector-based rate limiting of that traffic which is supposed to go through your firewall and reach your service. Here, once again, you may drop good and bad traffic collectively. So the DDoS techniques so far are limited in that the traditional methods do not allow you to do intelligent mitigation. I'm going to show you some intelligent mitigation capabilities that you have available, the new toolkits. Right? Okay, so I stop here for one moment and I ask you this question, just to belabor this point. Let's say your strategy, you had a traditional DDoS device and you were tasked with coming up with thresholds for each vector. Who here can tell me how many TCP push packets should be allowed through this point in the network at this moment? What human can come up with that number, right? So this doesn't work, but this is what we had available so far. So I'm going to now show you two very important techniques that are state of the art. One of them is, let's do auto thresholding. So when we do auto thresholding, for the people in the back, this chart may be difficult to look at, but let me explain it to you. What we're doing is, for every vector, every 5 minutes, we are computing this green line. And this works a lot better if I could animate. So this green line, just look to the left of my hand. And if you're looking at the dashboard, you just keep seeing, oh, this is what the current threshold should be. This is what the current threshold should be, et cetera. So it's a rolling graph, right? So what you see here is this yellow line is computed for every 5-minute period. In the next slide, I'll show you how we actually do that computation. One technique for doing that computation that we use, every 5 minutes, we're figuring out what the threshold should be for a particular vector. For TCP push, what should it be? For TCP SYN, what should it be? For UDP, what should it be, right? And there's another thing that we are looking at. We're looking at what is the stress on the service. So we're computing the vector, the threshold for the vector, and we're constantly also checking what is the stress on the service. Now, when the stress on the service goes up above an unacceptable limit, at that point, I know that I must be under attack. And I start seeing that the current EPS, the current events per second, so packets per second, the current packets per second are way above the computed threshold, right? Now, imagine if this was just set statically and you did not have this stress computation at all, what would the device do? The device would say, hey, I'm just going to start dropping this current packets per second. They're crossing the set threshold, going to start dropping, right? But if it was a legitimate increase in traffic, you actually start causing the DOS. But here, you're protected against that error. Why? Because I'm not going to drop anything until the stress is such that I know my users are going to have a bad experience, right? So when the packets per second start going up and much higher than the threshold that the machine has computed, then I start doing the mitigation. And when the stress on the service is back under control, I stop doing the mitigation. And so this is a dynamic mechanism, even if you are thinking about using thresholds per vector. Using this auto-thresholding mechanism is much wiser than having to do it by hand, right? Now, how did we compute this threshold? So I said that we computed every 5 minutes. Very busy slide, so let me help you through this. So this, what I've done here is, every tiny little rectangle here is a 5-minute slot. This is in the first hour, second hour, 24th hour. And then I've broken it down by days: Monday, Sunday, Saturday, previous day, et cetera, right? So this is the 5 minutes for which we want to compute what the threshold for every single vector should be, right? So you do this per vector. There are 118 different vectors. So the machine is looking at traffic that is matching all of those. I just made up that number, 118, 200, 400, some number of vectors. So the machine is tracking each vector and coming up with the threshold for each vector. So what is the mechanism? So for this 5-minute period, I want to compute what the threshold should be. And the way I do it is I look at what happened in the last hour. This is my current trend. And then I look at, I'm in hour number 2. I'm a 5-minute slot in hour number 2. What happened in hour number 2 yesterday? Then I look at, hey, I'm a 5-minute slot in hour number 2 on Monday. What happened in hour number 2 on previous Monday? And all of the Mondays before, for the last 52 weeks. So that is historical information. So I look at the current trends, I look at the historical information, and I use these two inputs to compute my appropriate threshold for this vector, right? This defends against, now, I weigh the current information a whole lot more than historical trend. Why? Because marketing may have done a campaign, and you may be expecting to see a legitimate increase in traffic, right? So the current trends, what happened in the last hour, what happened yesterday, these are very important, right? Now, we are humans. We think in terms of days. The machine is thinking in terms of minutes, seconds, nanoseconds, right? So this 5-minute period is like an eon for the machine, right? So does this make sense? The computation of auto-thresholding, and it is a better scheme than trying to set the thresholds by hand. Yes? Excellent. Okay. One other technique that people often think about when they think about DOS is they say, one way to deal with DOS is just scale. If I'm under attack, I just spin up more machines. I'm virtualized, I'm in the cloud. Someone is attacking my service, I just start spinning up machines. Valid scheme. And again, the spirit there is, I don't know who to drop. So I'm just going to absorb the DOS. I'm just going to increase my capacity, right? The valid scheme, but very expensive. And not actually that easy to auto-scale quickly. But I mention it here because it is a technique that people think about using. And our goal in this session is to give you all the techniques that we know of with our opinion on whether it's a good technique or not, right? So now I want to show you your strongest power, machine learning. So with this, it's a scalpel. So it's very surgical. And what you can do is two things. One, you can be very deterministic about the
identification of attack before you mitigate. That way you don't cause false positives. And then the second thing is, with machine learning, you're baselining the traffic, and when you see that the service is under attack, and how do you see that? Stress. How do you see that? You're constantly watching the stress on the service. When you see the service is under attack, you stop learning. And at that point, you start looking for the anomaly, right? And so the techniques are now available, and we implement them. Brendan told me I'm not supposed to sell anything. So I'm just talking techniques, right? So the techniques are available. We implement them where you can rapidly discover the anomaly against the baseline that you have been generating, right? And what that does is, instead of creating static vectors, like you said, for TCP push only allow so many packets, this is creating dynamic vectors. And the vectors are much more precise. It's not just a TCP push. You will see the signature will have various characteristics of IP level characteristics, TCP level characteristics, and HTTP level characteristics. So the signature will be extremely precise. So let me now demo this strongest power quickly, and then we'll get into how does it work. What is the technique that is underlying this capability? Go ahead and start. So while the video starts, what you're seeing here is 14.0, and we're protecting a web application here. And notice, I did not set up any static vectors. I just told the system, please protect this application. It has a particular IP. We see the stress was low, and we're watching the traffic that is going through the system, right? And everything right now looks hunky-dory. Now the hacker wakes up. I'm going to create a brand new attack, use all kinds of attack tools. If you went to Nilesh's lab, he'll show you how you can create attacks for which signatures do not exist. And this one happens to be a layer 7 attack, and the attacker has attacked, and now they're drinking their coffee. And they're going to go to your site and see what happens. But before they catch you, the system caught it and said, hey, this application's under attack. The stress is at 100 out of 100. So before the users begin to suffer, we already caught that the application latency is going down, right? And it discovered signatures, and it used those signatures to do mitigation, and the stress is under control now. The users will keep going to the application successfully. And what I want to show you, get ready to pause, not just yet. What I want to show you is now, pause if you can. It's hard to, yes, yes. Okay, this is good. All good. So now, what I want to show you is, look at what the signature looks like. So HTTP accept encoding header, that parameter. The HTTP cookie header, HTTP URI length, HTTP headers count, HTTP URI file flashes like something, hashes like something. HTTP X forwarder set or not set. Look at how specific that signature is. And I'm showing you our strongest power. So I'm showing you the specificity of the signature at layer 7. We generate these signatures also at layer 3 and layer 4. If you only have UDP traffic, if you have TCP traffic that's not carrying HTTP, then we will generate these signatures at layer 3, layer 4. There you will see things like TTL so much, the source IPs, a particular portion of the source IP is incrementing in a scripted fashion. So we start to discover very specific aspects of the traffic at layer 3, at layer 4 as well. So, okay, we can play this out. So now, the question I have for you is, what did the user have to do in order to detect and mitigate this attack? What did you have to do? Nothing. Just, so we took care of the work, right? Now, in reality, what most people end up doing is they put this technique in detect-only mode. when the attack comes, they quickly go and tell it, okay, start mitigating. Because as humans, we still haven't learned to trust the machine. And maybe we should never trust the machine. Maybe we should always keep control. But the machine is giving you something very specific, and the machine is ringing the bell before your users begin to complain. This, along with all of the traditional techniques which are basic, okay, rate limit and source IP shun, fine. That's what was available. But this is what the real ideal solution is. And the next slide. Okay, so now what I want to do is actually explain to you how this works. And a quick story, by the way, just so you start thinking and start waking up a little bit. I was at Black Hat the other day. I offered this explanation to every hacker I could find. And then I said, hey, if you can just come back to me and just theorize, you don't even have to actually do it, but just theorize how you would defeat this scheme. And if I cannot counter your argument, I will give you a reward. I was throwing up $500 out of my own pocket.
We'll give you a Starbucks gift card.
Yeah, not F5, not F5 thing, but I mentally I was, if I'm such a geek for this math, if somebody is willing to engage in a theoretical discussion on how you would defeat the scheme that I'm about to show you, it's worth it for me personally to give that person $500. So I want to go over this technique, and then let's take a 30-minute pause and see how we would defeat it. So what's going on is every one of these little blue rectangles here, it's a packet on the wire. And right now, what's going on the wire is I'm looking at every single packet. There could be millions of them. And I'm looking at each one of them. By the way, that's an abstraction. I'm also an electrical engineer and a physicist, and so I can tell you it's really signals going back and forth, right? So packet is an abstraction, right? So at any given point, there's only one signal on the wire. But anyway, so in our human instance, 1 second, millions of packets on the wire. So what I'm doing is, if you think about the packet, if you think about that abstraction, draw a big rectangle, right? Just work with me, visualize for a moment. Draw a big rectangle. So it's an IP packet. So what's it going to have? It's going to have IP level fields. Source IP, destination IP. It'll have TTL, the type of protocol that it's going to carry, correct? You can imagine that. Now, that rectangle is going to have a payload section where I'm carrying some TCP. And that will have its own fields. Source port, des port, flags, et cetera, et cetera. And the TCP payload is carrying HTTP. And HTTP is going to have its own fields, right? So in this rectangle, what I really have is a bunch of fields from source IP, dest IP, source port, des port, HTTP headers, the URL that is being requested. All of these things are going to be fields. So what each one of those fields, so I give you examples of some layer 3, layer 4 ones here. TTL, source IP, des port, other L3, L4 fields. Each field, we call it a predicate. A little bit of math here. Call it a predicate. Now here's the cool thing. Each predicate has a universe, a limited universe of possible values. So for example, if you think about TTL, that's the easy one. 1 to 255. IPs are more complicated, right? So the IPs, you can have millions of them. With IPv6, even more. So each field is going to have a universe of possible values. So what we do is we divide that universe of possible values into bins. So for TTL, it's small enough, that universe of possible values is small enough that for each value I have a bin. So TTL1 has its own bin, TTL2 has its own bin, etc. In case of IP addresses, I have to hash them and place them into a bin. And what I'm able to do with this is I'm now able to see for all of these packets that are coming on the wire, what value does each of the field takes, And based on that, I go and update the bin for the predicate that I watched. I have 3,000 or so such bins. I don't know the exact number, but it's in thousands. So I'm keeping track of thousands of these bins as I look at each one of these packets. So this packet, let's hone this in with our view on one packet. So this packet here is saying for the predicate browser type, whose values are very small, Safari and Firefox and IE and Opera and Chrome, this packet is saying I'm using Safari, so the Safari bin goes up. But this packet is also using this URI and this referrer value. So those bins are going up because of this one packet. Now we're doing that for every single packet, right? Who's this happy guy here? That's the happy application. The stress is low right now. So I bring you back to the concept of stress. All of this counting and statistical analysis is not useful if I have also an accurate determination of attack condition, which I do with stress, right? So I'm doing all this counting when my server and my service is happy. And so I call it peacetime. So in peacetime, I'm doing all this learning. Now, that was just this instance. I'm doing this from the moment you start the feature up until now for every single packet that's going on the wire. Whoa, that's a lot of data. You can't even hold that data in memory, let alone analyze it in real time, right? And this was why most people could not perform this kind of machine learning-based determination of anomaly, because baselining was difficult, right? So we've got patent-protected algorithms that will simulate as if I'm storing all the data without having to store the data, right? So by looking at whatever analysis I did of historical info plus what's happening right now, I can be 90% accurate in doing my analysis as if I was holding all the data and analyzing it. And that's the trick. That's where the patent-protected algorithms go into play. So now what I'm doing here is for every one of these bins, I'm coming up with these thresholds. And I show you this is the threshold for Chrome, this is the threshold for Opera, this is the threshold for IE, threshold for Firefox. And then for other predicates, I'm also coming up with appropriate thresholds for every single bin, right? And when I'm under attack, so I'm under attack now, and how do I know I'm under attack? Well, my server stress just went up. The latency from the server has just gone through the roof. So I'm under attack, as I showed you in the demo. Stress is 100. Okay, I happen to know that these red packets are the ones that are causing the attack. But the machine has to figure that out. So how does the machine figure that out? Well, the machine sees the Chrome bin, the Chrome threshold, it's being crossed. And at this point, by the way, because I'm under attack, I've stopped learning. I've gone into detection mode, right? And so the Chrome bin has been crossed, so I know attackers using Chrome. But so are these good people using Chrome. So I can't just punish everybody with Chrome. Then I would be punishing good along with bad, right? Which is what we don't want to do, the whole premise of this discussion, right? So I also look at what other thresholds are being crossed. Okay, so here, you know, this particular predicate, this particular bin, that threshold is being crossed, and so on. So I look at every other threshold that is being crossed, and based on that, I'm able to compute this very specific signature. So Chrome was being crossed, the GET method, the HTTP request method threshold for GET was being crossed, etc. So by looking at all the thresholds for every single bin, one of those 3,000 bins, I'm able to compute a very specific signature. All right, so what does the hacker need to know to defeat this? Huh? Your pattern. Hacker needs to know everything that all the other millions of users were doing. and have been doing in the past in order to defeat this scheme. And I did not lose even $1 during Black Hat. Right? So this is the technique that you also have available. Along with the basic techniques, you have this technique also available. Okay, so with that discussion of various techniques that are available, I hand it over back to you.
Yeah, so now we're going to talk about where to start applying and where we can look at applying these techniques, right? So we talked about auto scaling, right? You can, with proper capacity planning, you can scale horizontally or vertically, right? Additionally, you can do rate limiting on the servers or prior to the servers or from the connection management device like an ADC, right? Pushing that problem further downstream, you can start managing your connection tables, right? You've got eviction policies. You can get rid of stale, bad flows or slowly performing flows. SYN cookie challenges, right? So we actually don't even try and build a connection table entry until there's a challenge response back from the client, right? You can still do your hardware rate limiting, but once again, you want to be more surgical. Firewall ACLs, you can do IP intelligence, right, where you've got a constant threat feed coming in and you can identify certain bad actors that may be causing stress to your server, or maybe they just don't participate in your server business. If you have a lot of cloud client traffic coming in, it may be a bot network that's trying to come in versus a real client, right? So being able to limit that. Adding hardware assisted for heavy computational problems that need to be solved. SSL hardware offloading. Bot mitigation. Once you're inside and looking at layer 7 attacks, being able to mitigate the bot traffic, right? API security can be applied here. Layer 7 machine learning, this is a great place for it. Why? Because out here, are you decrypting SSL? How many times are you going to decrypt SSL and re-encrypt it and decrypt it and re-encrypt it, right? We do back-end for PCI environments, but do you want to have a third place, fourth place? How long is your tool chain? And then, of course, you've got tools like IDS, IPS, before and after encryption. In 14.0, we released a new IDS, IPS signature. Thank you. We have 0 days, right? All of your mitigations can be done there. iRules, so most of you are F5 familiar, right? We've got iRules, often get published for 0-day mitigations. Moving it a little bit further upstream now, we still have to manage our memory and our flow management, right? We have downstream devices that may not be as powerful. Maybe it's a lower risk application and you didn't invest in much in it, so the firewall connection table is kind of small. You can leverage inline devices here to try and manage those connection tables so they don't get overwhelmed. Look at bandwidth rate limiting, right? If I've got a small box that's got a 100 meg connection or a VM that's got a 100 meg connection downstream, I can rate limit at the edge and allow that traffic to get through, but not penalize everybody else that in those shared risk models, right? Once again, can you decrypt here? Yes. But PFS-enabled ciphers, right? TLS 1.3 mandates PFS-enabled ciphers. You have to be a proxy. You have to be inline. So once again, how many times within your security tool chain are you going to decrypt and re-encrypt traffic to provide any mitigations? And then, of course, you have your net flow, your flow detection and mitigation. Your remotely triggered black holing BGP flow specs. So you're providing these mitigations on the router closer to your edge so they're not traversing your network infrastructure. And then lastly, are you providing signaling to your cloud provider, right? Telling them about bad actors so they can block on their edge, right? And then cloud scrubbing provider redundancy, right? Back to that shared risk model. If you're not the #1 customer and they're not willing to sacrifice their network for you, do you have a backup plan? And then how do you go through and assess your security posture, right? So have you done an application assessment? Have you built those baselines? Have you identified those east-west dependencies, right? Have you built the trends and you're prepared for that next marketing campaign? Have you identified all of the application infrastructure and all of those components? There's been a lot of outages when DNS went down for the internet, right? Everybody thought the internet itself went down. That's the application experience when DNS goes down. And then, of course, that shared service infrastructure, right? We don't typically do per app firewalls, right? Routers, switches, per app routers, not very often, right? So assess each one of those points in your shared infrastructure. And then lastly, do you have an operational plan? Is it really a DDoS? Do you know and have a plan in place to identify an application outage versus a DDoS? And how do you have that escalation set up, right? Who answers the phone for a DDoS? You have a DR plan. Do you have a DDoS plan? You're testing your DR, most of you are testing your DR exercises once a quarter maybe for really important applications. Are you testing DDoS? And lastly, do you have a list of all the contact numbers for escalation? In the end, do you also have the right tools? We've talked about the sledgehammers, the surgical medications. Do you have them in the best location? Because in the end, that really smart guy said, DDoS is all about application delivery. Thank you.